On this map, I've placed all the STL algorithms as of C++17, and I've grouped them by region according to the logical relationship they have, right? The rest of this talk will consist in exploring that world. But before diving in, we can note a few things while looking at it from afar. The first thing we can note is that for each is just one of them on one island lost on the middle of the ocean. So it's just one of them. What we can know also is where most of them are. You can observe that the largest region on that world is over here, and that's the lands of queries. We call that queries because all those algorithms that live here, they just read into the collection and extract some piece of information, and they don't actually modify it. I don't know what you think, but I would have thought that most algorithms would somehow change the collection, like sort or partition or whatever. Like, they are there as well, but most of them, they're just read-only operations. I suggest that we start our journey by the other end of the world from for each, down here on the algorithms on heaps. So what is a heap to begin with? A heap is a data structure that looks like a tree, but that has a property. It's that every node must be smaller than its children. I think it's called that because it kind of like looks like a heap in real life. Like the small ones are at the top and the bigger one is at the bottom. It's better having a heap. Now you can observe that the heap on the right of the picture is the other way around, right? The biggest element is at the top and every element is bigger than its children. That's a C++ heap. It's called a max heap. The relationship between a parent and its children is the parent is bigger, right? So it's the other way around from the heap from real life, but you know, we developers don't really live in real life anyway, so does it really matter? I don't think so. So one interesting property of a heap is that we can squash it down into a range like that. One more time, more slowly. To squash down a heap into a range, we take the first row, which is just the root of the tree, and then the second row, and then the third row, and so on and so forth. And when we do this, there's this nice property that it's arranged, so we can represent it with a vector, for example, which is quite convenient to work with. And also, to go from a node to its left child, it's essentially taking its index and multiplying it by 2. It's nearly that. So it's a way to represent a tree into a range. If we have a range, we have a beginning and end, and we can use STL algorithms. So the first thing we can do is taking values that are not particularly a heap and rearrange them so that they respect the heap property to make a heap. To make a heap, we use std make heap with a beginning and end, and that rearranges the element inside of a collection. That's our first algorithm of the day. That's 1 down, 104 to go. I forgot to mention, it's 105 STL algorithms in less than an hour each. Just making sure we've got the same understanding here, right? No, I'm joking. Don't worry. Well, either way, you'll find out. Let's move on. What we can do with a heap is add something to it. Independently from C++, to add something to a heap, we put the new thing right at the end, and it might not be its right position because it may be smaller than its father. And the way to add it to the heap is to swap it with its parent until it reaches its final position, right? Now, to do that in C++, we can squash down the heap, right, to represent it as a range. Say that it's a vector. We add something to the end, and then we need to do we need something to make it bubble its way up to its final position, and that's push heap. Now, push heap just does the same thing we've seen with the tree vision, but in the range vision. Now, to remove something from a heap, well, there's this thing with heap. Why do we use heaps in the first place? Is to be able to get the maximum value of the collection in not so much time, in constant time. Like the heap, the max element of the collection is just the front. So this is what we access, and this is also what we allow to remove. To do that, we swap it with the last one. That's what pop heap does. At this point, the range in yellow is probably not a heap, because that's the one at the end that was probably one of the smallest ones that was at the beginning. So we need to make it bubble its way down to its final position, and that's what pop heap does. And if we want to actually remove that value, we pop it back from the vector. Now, if we don't pop it back from the vector, but leave it here, and do that again for the part in yellow, the shrinking heap. If we do that over and over, at the end, we'll get, can someone see what we'll get at the end? Yeah, right, a sorted collection. So that's a way to sort a collection, and that's what sort heap does. Talking about sorting, this is the region around the corner, the shore of sorting. So let's see how to sort with the STL. Well, the simplest way probably is std sort. That takes a collection, begin end, and rearranges them so that they're in sorted order. Okay. Now, if we only want to sort the beginning of a collection, as we saw in depth in Fredstock, we can just partial sort the thing. So partial sort takes a beginning and end, and sort of like a middle, something inside of the collection, and sorts the collection from the beginning to that point, and the rest is in unspecified order, right? So the left-hand side of the collection is what would be there if it was completely sorted. Now, to sort just one element, that's nth element, which takes a begin, an end, and something inside of the collection, and puts at that position inside of the collection the element that would be there if the whole thing was sorted. And for the rest, everything that's on the left is smaller, and everything that's on the right is not smaller. There's sort heap, which we've mentioned with repeatedly calling pop heap, and there's in-place merge. In-place merge is the incremental step in a merge sort. So we've got a collection that we can mentally think of as two halves, and merge sorts. So the two halves are sorted, and merge sorts combines the whole thing into a sorted collection. So that's about sorting with the STL. Just further up the shore, there's the region of partitioning. So what's partitioning in the first place? To partition a collection is to look at it through a predicate, something that returns a Boolean. Here, our predicate is being blue. To partition a collection is putting all the blue ones at the beginning and all the not blue ones at the end. Of course, it works for blue and red and yellow, and actually any predicate there is. The border between the blue ones and the not blue ones is called the partition point. That's the end of the blue range, and that's also the begin of the not blue range. Can you see that? Okay. That's called partition point, and to retrieve it from a partition collection, there's std partition point. Right. If we take a step back on that part of the world, that was the land of permutation, the place where elements move around the collection, even if they don't change value. We've seen heaps, sort partition, and there are a few others that we'll go through quickly. There's this permutation that takes the element at the end and put it at the bottom. Put them at the beginning, sorry. That's rotate. Another way to change the order of the element of a collection is to do that randomly. And that's what std shuffle does. So std shuffle takes a collection with elements in a certain order and takes something that generates random numbers and rearranges the collection in random order. There is an order we can define on permutations. Like given a set of objects, given a collection of objects, we can order them, order all their possible arrangements, and an intuitive way to see that is thinking about an alphabetical order, right? So in this collection, 1, 2, 3, all the way to 9, the smallest one, if those were in a dictionary, would be that first one, 1 all the way to 9. And the one just after would be the same thing with a 9 and an 8 swapped together, right? And so on, and the largest one would be the one at the bottom here, from 9 down to 1, right? If you have a collection in a given order, any order between the smallest and the biggest one, next permutation, which takes a beginning and end, would rearrange it so that it goes to the order that's just after it, and pref permutation to the order that's just before it. That's interesting if you'd like to do something for every possible arrangement of a collection. You can repeatedly call next permutation until you've cycled back to the beginning. And finally, the last one is reverse. That reverses the element of a collection. Right, so we've been all around the lands of permutation. Just in the corner of the map here are the secret runes. The secret runes are things that you can combine with other algorithms to generate new algorithms. I call them runes because it's like going to see runes to augment your powers, and also because I find that kind of cool as a name. So let's call them that purpose of this presentation. We've seen all the algorithms that go with the stable rune. So stable, when you tack it on to an algorithm, it does what this algorithm does, but keep the relative order. Think about partition, for example. It put all the blue ones at the beginning, that's for sure. But maybe in the process, some of them got swapped around. With stable partition, they all keep the same relative order. Same thing with stable sort. The is rune checks for a predicate on the collection. We know what sort, partition, heap means, or is sorted, is partition, is heap, returns a Boolean to indicate whether it's a sorted, a partition, or a heap that we're looking at. And is until returns an iterator that's the first position where that predicate doesn't hold anymore. Right? So for example, if we have a sorted collection and we call is sorted until, we'll get the end of that collection.